Okay, so the way you need to start is to make an account on our server. There is the URL for the server, and there is the code. So what the code allows you to do, if you provide a made-up name, oh, I see we've got a chat session. Hmm. Oh, thank you for your talk. Okay. Yeah, subcycling has been implemented, but as I say, it's not yet in the current release. And the URL, Behan, that you typed is wrong. It's ETK1, not ETK.
Yes, I just realized that. Yeah.
All right, so I'm going to just take this and I'm going to copy this into the chat,
Yeah, yeah, that's a bit.
and everybody can try to work on that. And you know, once you have your login account, if you could just raise your hand with the Zoom interface, and we'll see that you're ready. Usually, this just takes about 5 minutes or so. And I'm going to switch what I'm sharing here to this. And when you log in for the first time, what you should see is a screen that looks approximately like the one in front of you now. You should see the Einstein Toolkit Meeting, um, and you should see this. There should be a notebook, a 111 menu.ipynb that you can click on, and when you click on it, you should see this. And as I say, once you see this, please go to your interface and raise your hand. I see one person.
There are seven actually.
Okay, the way the interface is showing. Here we go. Now I can see them. I had
Yeah.
just had to change the way I was looking at people. Uh, I'm gonna give people just a minute or two so we can get a few more. 12. We can definitely handle 12. We can't handle 57, but we can handle 12. We can handle a few more though than we currently have. All right. I'm going to start talking, and if more people get their login working, they can join in. All right. So the first notebook that we're going to go to is the Cactus tutorial notebook. This is the standard notebook that we use um, for teaching people about Cactus. It's a step-by-step guide, and all the compilation and stuff has been optimized on this machine. So, you know, it may happen that if you go to install Cactus yourself, you might have to fight with it a little bit to get certain things to install correctly. Before you start fighting with it, you should probably consult this list and install the base components. We've got little like DNF install for Fedora and apt install for Debian flavor. That if you put these in, it should streamline your process. I can't guarantee it will be, you know, frustration free, but you know, installing large software bases is always a challenge. Okay, so then there's a notebook setup. We've got a couple of little bits of magic that we have in place for you, and and those are encapsulated in this. How many people is anybody unfamiliar with Jupyter notebooks? You can just speak up, or you can type something in the chat or whatever. Do I need to explain Jupyter Notebooks, or is that something that everyone understands at this point? Okay, everybody understands it. All right. So this is basically how you set it up. We've got we've got a magic called %% bash, which we supply. And the first thing we're going to do is we're going to install the Cactus, a complete Cactus setup from a tarball. Now, the idea here is doing the actual download of Cactus from scratch would take longer than we have probably for this tutorial. So what we have is an optimized process where we put all the files in place, pre-built with the modification times what they need to be, and then we can go through the motions of the download and install. And you can see how all those parts work, but they'll work much more quickly than they would if you went from scratch. And as you can see, mine is almost done already. It has this nice little progress indicator for you. And again, speak up at any time if you have a question or if something isn't working right, and we'll try to help you. One of the things that happens once you get a significant number of people involved and they're using this big tarball is that it becomes a little slow because the file system gets burdened. But you know, um, as I say, I/O is a standard challenge for numerical relativity. So this is almost done. It's taking just a little longer than I expected, but it's okay. Okay, that's done. Um, now we have this auto magic, which allows us to have our CD command work without any exclamation mark or %bash bash or other things. If I do a CD inside a %bash, it won't be remembered beyond the cell, but I can do it. I can do it either here if I want it to be remembered, or I can do it in here if I don't care for it to be remembered. So the first thing we do is we download the get components script. Now, if we were building this tool today as opposed to 30 years ago, this would probably be submodules from Git, but it was not today. I mean, this was built 30 years ago, and there was no such thing. So this is sort of a poor man's submodules, if you will. And the notion is it can download different components from different repos all over the world. And the idea was we didn't want to have the Einstein Toolkit be centrally controlled by just one group of people, right? If you contribute a thorn to the toolkit, you don't hand it over to us to be managed necessarily. I mean, I guess we could do it that way. But the point is you can retain your ownership of your repo and your piece of the toolkit. And so anyway, you download Get Components, and Get Components is capable not only of downloading Git, but it can use Subversion and probably even CVS, although that hasn't been tested in a decade or so. So it was the idea it could work with multiple different kinds of repositories. Now, the next thing to do is we're going to get a thorn list. And this should say ET user here. If yours does not say ET user there, please change it. Anybody need to change it?
Yes.
Yeah, sorry about that. Yeah, just put an ET user there. And once you have an ET user there, it should work fine. And then you should see, what the heck? You should have seen fewer things than that. All right. And then you go to the Cactus directory. And the first thing we're going to do is we're going to set up SimFactory. So you run this command. You typically run SimFactory bin sim setup silent, and it prints out something very similar to what you see here. It's going to identify your machine as Slurm Jupyter. It's going to use a config for that, and and then it will just SimFactory will know what to do with your machine from that point on. So the next thing we're going to do is we're gonna build Cactus, and this is going to make use of Slurm. It's going to send your build command to one of our various compute nodes, and it's going to use two cores to build.
Steve, you might
And
also bet to let people catch up. Mine is still 60 stuck at 62% in unpacking.
oh, all right, okay, I can slow down. Um, I will wait for a few minutes until people catch up. Let me know when you're unpacked, Peter.
Yeah, well, it's suddenly got going again. It's now at 87%.
Good.
Okay, I'm finally unpacked.
Great. Let me just check something here. Something is bothering me. Oh, shoot. Shoot, shoot, shoot. I have a problem. I made a mistake. So you test these things extensively and you still miss things. In this case, I have a wrong thorn list. All right. So what I'm going to ask you to do, let's see how this is going. Yeah, this is I have just updated the thorn list. So I'm going to ask you, let's see, I can go to kernel, I can do interrupt. I'm going to go back to this step and rerun it. And this is what you should have seen. So if you've already run this step, I'm going to ask that you rerun this step. And then you don't need to well, you don't need to rerun the other two, I guess. And then you can just go back and rebuild. And this is going to take a while because even though everything is pre-built, it's going to take a while to it's going to take it a while to figure out that everything has been built, and it is going to relink your final executable, and that will take some time. So you can scroll down here on the right. And we used to have a capability of keeping this locked to the bottom so you could just watch it, but they upgraded Jupyter and took that ability away from us. So you have to keep it updated yourself, and it's going to take It's going to take just a few minutes here to look at. So I'm just going to talk a little bit. Well, okay. Are there any questions or are there any problems that people are having apart from slowness? No, just slow. Okay. Well, all right. Yeah, just slowness. Yeah, alas. It's one of the things that happens once you get a certain number of people doing something. Um, so if I run top, our load is 30. Okay, that's why we're slow. And if I look at SQ, I see we've got 3 people building. $30. All right. So one of the things about, as I say, because this server is not necessarily built for 57 people, uh, what I, even if some of these tutorials, and some of them are going to take longer to run than others, you can always run these on your own after the workshop is over or in the morning, or have them going in the background during other talks. And even if it's slow, it will get there, right? The tortoise will eventually cross the finish line, and you'll be able to work through it. We're going to try to keep this cluster available for a week or so after. It might be that I reduce the number of nodes after a number of cores available on the server after the workshop is over, but we're going to try to keep it up so that you can continue to experiment with it. Um, so as you see, what this is showing mostly is that it is building a few things, which surprises me because I know I tested this and it didn't build things, but whatever. It's building a few things, and but it's mostly just checking the status of things and finding that they're already built. Okay. How are people progressing? Let's see. We've got we've still got only 3 people building, so I guess most people are still untarring. Is that the case? 35%. Okay. All right. I'm gonna pause here for just a little bit and let people catch up. Um, I realize what I did wrong now, but okay. Uh, I told you the wrong thing, but it's fine, I guess. Oh no, it's not. Okay. All right. I'm gonna make this correction one more time. because ET user was not the right thing. It should have been home ET user. That's the one it should have been. I confused myself. And okay. Uh, I'm going to restart my kernel here so I can redo this build, and I'm going to rerun this cell, and then I'm going to rerun this cell and this cell and this cell and this cell.
Should we do this as well?
Yeah, please do.
Okay.
I'm sorry. You know, I spent so much time testing this and I still managed to confuse myself. So let's call this a lesson in the importance of testing. I mean, you're probably never going to do as good a job as you want to do, but the more you test, the better off you'll be. It doesn't ever make you infallible. How is the unload processing? Let's see. We got any? If we got any more people? We've got fewer people building now. You're all still stuck loading, I guess. Load is 30. Is that correct? Yes. Okay. So you have the advantage that you can fix this problem without having to start rebuilding, like I did, by putting home ET user there on your get components line. And then you should just see this little bit come in, and it should all build fine. Look at that, all this beautiful stuff that's not building. I'm building some things because, of course, I touched files. Now, one of the ideas behind this untar is even though it's slow, it's still faster than doing everything from scratch. And if your cactus build gets corrupted in any way, if you manage to break it and wreck things in some fashion, you can just rerun this one cell and it will reset all the files to be what they're supposed to be and have the modifications the times that they're supposed to be. And that's just a reset button that you can use if you ever need it. All right, and my build is running. And let's see if we've got some more people to build state yet. I'm hoping that the fact that it's now down to me means that somebody has succeeded. Has anybody succeeded in building? I mean, you can speak up if you have. Peter, did you get it to build? Or are you?
And not yet because I went back and restarted the kernel and started from scratch, and I'm now
Okay.
unpacking
All right.
again.
All right. You're unpacking again. Okay.
But it's just about to
Um,
finish unpacking.
all right. What I wish I had was some kind of progress bar where I could see where everybody was in their unpacking state. I mean, I have this. I've got Gabrielle D is back in the compiling phase. So this cluster is a small Slurm cluster built on Docker Swarm, which we can replicate on, on any hardware that we happen to come across, and we could build this tutorial almost on any set of machines you could come up with. And I am actually doing compiling, which is unfortunate. I guess this is because I didn't restart from scratch and re-unpack. And I made a mistake with my get components. All right. So let's talk a bit about this line here. So when we want to build with SimFactory, by default, it's going to build a configuration named sim, right? So if I go and I look at my source tree, if I go into my Cactus directory, what Cactus is going to do is it's going to have the following directories, right? It's going to have arrangements, which is where which I can go into the arrangements and find all the thorns. It's going to have an exe directory, which is going to have when everything is built is going to have my Cactus build my Cactus executable, and it's got a configs directory, and everything happens under the configs directory. So Cactus has an out of source build concept, and that is our source code is all under arrangements, and our build is all under configs and exe. And under configs, we have a config name, and you can build different configs. And the idea was that you can build Cactus for profiling, or you can build a highly optimized Cactus, or you can use some other compiler flags, and you can build the toolkit in different ways and keep them all separate from each other. So you can have if you have a profiling build, you can run that and figure out where your hotspots are or whatever, or you can just run the other one. And so that's part of the design and the modularization and separation of concerns that was built into the thing. So SimFactory by default is going to build a configuration called sim. You can tell it to give you can provide a config name here after the build if you want. You could put not sim or profile or something like that, and it will build a directory under configs with that name. The -J2 is going to tell you the parallelism that you want for your build. In this case, I've picked 2 because I wanted to support as many people as possible, but not be but still get some performance out of the build process. And then you have your thorn list. Now let's talk a little bit about a thorn list. The thorn list is the thing that allows us to glue Cactus together. So by default, when you unpack, you get everything in this thorn lists directory. And your thorn list looks like this. There's a bunch of different entries. So we have the basic release that everything is built on. We have a root directory is going to be cactus by default. You can override this with get components. And what you have is a pound is a comment in this file, but it's got its own little language, right? So we're going to have the target is going to check out under root. That's going to be what almost all of these have. It's going to have the type of repo, which is Git. As I say, we used to have different flavors of repos that we supported in the past, but Git has taken over the world, so that's pretty much all that's left. We have a URL for the repo, and you will find that while most of these come from Bitbucket, they can come from anywhere, right? These URLs can come from anywhere. You can provide a repository branch. You can, if you need your checkout to work with a specific special branch, you can do that. And I think there are examples in this file. In this file. And then it's got a name and some checkouts. But mostly the way the thorns look is like this, right? We've got an arrangement name and a thorn name. So the concept the cactus has is every thorn lives in an arrangement. So every one of these modules has its own sort of grouping that it lives in, and that means it comes from the same repo. So and we have different flavors. I told you about you could monitor your cactus run and modify it in real time, and you do that with Cactus HTTPD, which the Cactus executable actually builds runs a web server that you can look at your data and you can modify parameters in real time. And there are just a number of different thorns like this. And if you'd write your own thorn, you would make an entry similar to one of these, and we can show you how to do it if you get to that stage. And then you can add it to this list. And you can see it's quite extensive. There are many, many thorns in the Einstein Toolkit, many, many arrangements, many contributions to science from a lot of different people and groups. All right. We're still with 3 people building. Everybody is still downloading? Really? Load averages actually increased. All right.
I'm done compiling, Steve.
Congrats. Peter wins a star. He's the first one to finish compiling. All right, so SimFactory, let's see. So SimFactory, you can supply a thorn list. If you want to, with SimFactory, you can also supply what's called an option list. And when your cactus builds, it makes a copy of the thorn list and it puts it in config name thorn list. And so it just has a copy of whatever you used right here. So you don't have to wonder which th file you used to create your cactus. You can always just look right there. And likewise, there is a thing called option list. And option list is going to show you what compiler options and what flags and so on are being used to build everything. And so these would be your CPP flags, your C flags, your CUDA flags, your Fortran flags, right? And Cactus has got a large number of software dependencies. This is going to show you where it gets its Adios 2 and the Adios 2 libs it needs and the Amrex directory and so on. It's got all these different pieces that it can have, right? This particular option list is a long one. relatively speaking, because it's got a lot of these different modules are pre-built using a tool called SPAC. This particular installation is on a machine without GPUs, so we have Amrex enable CUDA equal no. I mean, while Amrex can use CUDA, it doesn't have to. It doesn't need to use a GPU, and it's capable of using other kinds of GPUs than NVIDIA also. Is there anybody out there who's absolutely new to Cactus? Okay, there's a lot of people. Okay, so I'm looking especially towards the new people. Um, how much of this is making sense? What questions do you have about things? I'd love to get some kind of dialogue going.
Just one person raised his hand. Javashri,
Okay, well,
do you want to say anything
yeah,
else?
yeah, Jayashri, just speak up.
Hi.
Hi.
For the first time working in Einstein Toolkit and using a Mac computer, it was kind of difficult for me to set up everything and get it start downloading and stuff. So that was kind of difficult for me.
It's going to be
And
difficult. I'm sorry, go ahead.
oh, sorry. And since this is my first time working, uh, since I'm not proficient with the coding aspect from even before, so it was kind of difficult to understand how to get it all working and running and stuff. Yeah.
I appreciate that. It's it's actually the case that well, with any large software project, right, especially one that's been around for decades,
Yeah.
compiling is going to be a challenge. That's one of the reasons why we have the tutorial server because we know how things work there. If you're running on a Mac, Macs are notoriously tricky. They do all kinds of awful things to you. They install the clam compiler under the name GCC, for example, which causes a lot of headaches. But I think with Cactus, as far as large software projects go, you have a better chance of getting up and getting going and learning about how these kinds of things work because we have a community here. And if you're having trouble, you can send an email to users@einsteintoolkit.org and people will help you. Will answer your questions. And we've got, as I said, we've taken some pains to get this information at the top of the source file correctly. Right, these different install commands. You've got your brew installs if you're using a Mac OS. I think you said you were using a Mac OS.
Yes, I am using a Mac OS.
Right. So if you're building on your laptop, you probably want to do these things.
Mm-hmm.
Um, so we do have some hand holding available for you. And as I say, if you're starting out, that's a good thing. With most other large software projects, that may be difficult to obtain.
That's completely understandable.
and I sometimes feel like even as long as I've done these things, it's not just Cactus. I feel like I spend most of my life figuring out how to install various things.
True. Yeah, but that was helpful. Thank you.
All right.
Still, we have 2 minutes before the break, 15 minutes break. It
All
can
right.
go on.
And then after the break, let's see, where are we? We have a 15-minute break. That's this one. Okay, and then we have the 15-minute break, and hopefully by the end of the 15-minute break, everyone will be
Yes, I think so.
functioning. So let's see. It is 9:30 here. That's okay. So it's 15:30. This is 1 minute to the break time. Correct?
Sorry?
1 minute to the break time?
Yeah.
All right. So we will reconvene at 15:45.
Yes.
Which
For your
is
9:45.
Which is 9:45 my time.
Yeah.
All right. And yeah, with regard to the Mac OS, we don't have a Mac OS systems that we standardly test on because none of the maintainers have one of those currently. But as I say, that's one of the many reasons why that particular platform is difficult. But as I say, if you have trouble and you ask, we can probably help you. Okay, so I'd like to return to our notebook. I see a few of you. Oh, I see something in the chat. Yeah, okay, so I see somebody has a job busy. Let me just take a look at. I don't understand. There's virtually no Slurm traffic. Okay. So our server is slower than I'd hoped for today's thing, but as you can see, this is what it looks like once it finishes building, right? So this is where the linking step occurred. Then it builds what are called the utilities, which only takes a minute or two, and then it's done. Once you're to that point, you can run a hello world thorn, and I'm guessing that for people out there, I'm hoping you catch up eventually. I was hoping you'd catch up sooner than you did, but this is the way demos and technical things go sometimes. So anyway, this is your first parameter file. Now, a parameter file pounds our comments just like Python. And there's a magic called %load that you can use that will load any file from disk. And in this case, we're using arrangements, cactus examples, hello world par, hello world.par. And that has a single entry, active thorns equal hello world. So if I load that thorn, I can just sort of, see it. And then the next thing I can do is I can run that thorn. And in this case, what I'm going to do is I'm going to delete. First, I'm going to delete the simulation from the simulations directory. If the simulation is already present, then SimFactory will spit out an error and not do anything. It assumes that you don't want it to overwrite an existing simulation with the same name. In this case, what I'm going to do is run something called Hello World. Now, create and run are two separate steps in SimFactory, and I can separate them. An alternative is create, submit. And again, create and submit can be separate steps. And we'll show you examples of all those things. But here's a create run. And when I execute this cell, what's going to happen is it's going to take my default configuration, and it's going to run it. It's going to create a simulation named Hello World, and it's going to run it with my default configuration, and it's going to use this parameter file, the one that I've specified with par file. And it is, when it works, we should see this, and that should happen soon. Part of the problem is I think this is a 20-core server on the head node here, and we've got 30 people, but hopefully as they finish their unpacking, things will get easier. And so the goal for this tutorial is to just get this hello world to run for you, and even mine isn't yet running. But we're gonna leave off at this point here. Running the single star simulation is something that I'm going to leave for Peter. And what we're going to do instead is we're going to switch gears, and we're going to go back to the main notebook set. And I want to take a look at creating a new Thorne X wave equation. And I'm just going to talk through this and hope that eventually the servers catch up. So this is going to have the same little magic at the start that we want to do. And what this Thorne is about how to write your own Thorne for Cactus. So you are at this point, you know, you have figured out how to compile and run Cactus, and now you want to see, you know, how you can make your own contribution to the source code that's there, or just experiment with making your own thing, or just figure out how that works. And we've got several different versions of this tutorial. We've got the one that I just showed you that we're going to work through, which is this one. But if you look at notebooks from previous years, we've got creating a new Thorne heat and wave equation without the X. And the idea with these two Thorns is they're for the carpet driver, for the old infrastructure that can't use the GPU. And the carpet X one is, the Thorne X one is for the new infrastructure that does use the GPU. But these are here in case you want to write something for carpet. I mean, carpet is still our most mature and best supported platform, whilst Carpet X is our newest cutting edge and doesn't have as many of the features as the old driver had. So what we're going to do here is we're going to, you know, this is just doing some setup. We're going to get our home directory. We're going to we're just going to tell the system where that is, and we're going to CD to that directory, and that's going to be, in my case, that's home Brandt Cactus. If you put something in single curlies like this, it will expand a Python variable with that name. So we're going to have some interplay in this notebook between Python and Bash. And then what we want to do is we want to create an arrangement name for this Thorne we're going to write. And then we're going to supply it a name. Now we've put it in this little cell in this way so that you can just sort of change it, and then the whole rest of the notebook adapts. But in this case, I've called it wave equation X, and I'm putting it in something called tests. And this particular Thorne is that we're going to build ourselves here step by step is very similar to WaveToy X inside the Carpet X repo. That one is a little bit different, and you can compare and contrast it later if you're trying to learn this framework. Okay, so I'm going to just set those variables. If you want to clear out everything that you've done and start over, you can just do that RM. We're going to create some directories now. And all this code is just to create directories. So we want to have arrangements. We want to have our wave equation X directory. And then inside that, we want to have a source, a test, a par, and a doc directory. And we're going to just do an ls. And we're going to make sure those are there. Now, I didn't start from scratch. I had this previously built. So I have some additional files. And we're going to build those together as we continue. Now, the first thing we're going to put in there is a README, and you should always put a README in there. You should put your author name and your maintainers and your license and so on. You probably won't do this when you start out, but documentation is one of those things that it's kind of painful to make, but you'll always be glad you did it. And these days, you can even use AI to get you started, although I wouldn't trust anything that it tells you. but it sometimes can cut down on the work of writing your initial documentation, so long as you don't trust it. All right, so now our Thorn directory has a README. Now here is the wave equation. I don't know if there are any of you who are unfamiliar with the wave equation. It'd be kind of hard for me to believe that there are, but anyway, the wave equation is a simple differential equation. It's just this, given a speed of 1 anyway. And the nice thing about the wave equation, there's several nice things about the wave equation. One is that it's simple. Two, that in certain regimes, Einstein equations become like the wave equation. Once you have the waves propagating out toward infinity, it's very wave equation-like. And what we can do, typically we don't like to have a second time derivative in something that we want to evolve, so we sort of split it into two variables in an obvious way. We have dt du equals k, and dt to k equals the Laplacian. And so that's the basic infrastructure. And then we have we can apply a number of different boundary conditions, and we're going to give you options here. But like here's one set of possible boundary conditions and one set of initial data. So we're going to create. So Cactus is based on its own little DSL. It's got 4 files, each with the suffix CCL for Cactus Configuration Language. There's interface, schedule, param, and configuration.ccl. And the latter one is optional in most cases, but for CarpetX, you must have it. Okay, so the interface.ccl looks something like this. And this is what it looks like for our wave equation. So first thing we have to say is what we're implementing. There can only be one implementation of a given thorn in your executable, but you could have, potentially several different thorns that implement something. And these are headers that CarpetX supplies to you, and you need to put these here to make sure that these are available to the modules that you write. And a lot of this is boilerplate that you can simply copy and use for your own thorns. By the way, feel free to stop me at any time with questions. I will try to pay attention. Yeah, I will try to pay attention to the comments, but it's perfectly okay for you to unmute yourself and speak up. So I don't think that we're gonna have a problem with that. Okay, so the next thing we're going to do is we're going to declare grid functions. Now, grid functions are field variables. They exist everywhere on the grid. So if I'm running a simulation across 1,000 thorns, across 1,000 nodes, I'm going to split up that grid function. It's going to be my XYZ space, and it's going to get split up over those 1,000 nodes in some way that the infrastructure will determine for you. In this case, we can supply some additional tags. So we can say that this is the state of the equation. Now, I know this is U rho, and up above we used UK. So just assume that rho means K. And what I'm going to say is I'm going to tell it what the right-hand side is. So one of the things we talked about how Cactus can abstract away things for you. And one of the things it abstracts is the time integrator, right? You can use Runge-Kutta 4, you can use Runge-Kutta 3, you can use Euler, you can use any number of things, right? And you're eventually going to tell Cactus which of those things you want. But all it needs to do to really accomplish this is it needs to know the right-hand side of the equation. That is, it just needs to be able to write out this, or in discretized form, this, right? It just needs to be able to write out these two state updates. So it needs to be able to compute this. And once it knows which variable is the right-hand side of K, or right-hand side of U, for example, and which is the right-hand side of K, then it can apply any time integrator to build any sophisticated time step you want. And Mustafa has got some kind of problem, which I can't quite see. Done. Oh, wow, great. Let me look over here, by the way. And there's my hello world. So when Cactus starts up, it draws this little cactus with ASCII art. It shows you the schedule tree that it uses to run, and then it should print hello world like 10 times. And if you see that, cheer for victory. You made it. How many people have seen this? Okay. All right. Definitely more than one. All right. But I'm not going to rely on this to catch up for the moment. I'm just going to plow ahead. Okay, so what we're going to do here is we're going to tell Cactus that for this group of variables, u and rho, for this group of variables u and rho, which are of type real, right? So each grid point is going to be of type real and not of type int, say. We want the right-hand side for this state to be this thing named RHS, right? So this tells Cactus all it needs to know in order to build the time integrator. And then we have an energy quantity which we can calculate. I don't think I make use of it in this tutorial. And we also have an error estimator that we can produce with analysis. And these things don't have a right-hand side or anything. They're just variables that we can use for analysis. Okay, so I'm going to create this file. And I'm going to ask if there are any questions about this file. Now, I realize that it might not make complete sense to you at this point, all the stuff that's in this file. But again, we are available for help in person during this week and on the mailing list after the workshop. So don't be afraid to speak up with your questions while you have our full attention. Okay. The next thing that we're going to create is our schedule.ccl. Now, the schedule.ccl is sort of our basic workflow that Cactus has, and the workflow looks like, run CCTK initial, run things at initial to start things up, run things in ODE solvers RHS to do a time step to evaluate a right-hand side, and then run other things at the analysis step. So every time you want to do an analysis, you can do that. And so also what you want to do is you want to specify in each of these steps what you write, what grid variables you write, and what grid variables you read. And Cactus is going to use this for consistency. So remember that ghost zone picture that I showed you before. So we've got ghost zones sitting around the edges of each of these pieces of our grid variables. And on the outer edges, we've got boundary zones. And what Cactus has to do is it has to make sure those things are always properly synced. And in this case, what's going to happen is it's going to if you get any of that synchronization wrong, it's going to try to automate it for you. But if the automation doesn't work out, then it's going to give you an error message, and it's going to let you know that something is not right. And this is a very important consistency check. If you get your boundary zones wrong, if you don't synchronize them exactly the number of places and times that you want, you wind up with very small errors that are hard to find. Okay, so we tell it that our language is C, which includes C++. We tell it when to run. We tell it what function we want to run at that time, what we write, and what we read. Now, here I'm using state and RHS, which are group names, right? That's this state. So that includes two variables, and RHS, which includes two variables. But if I wanted to, I could also specify those variables individually. I could say U, and I could say rho. Now, The other thing to notice is where I'm writing. I am writing the interior. That means not including the ghost and boundary zones. I'm reading everywhere. That means I must have synchronized ghost zones and boundary zones. The other thing is I specify which variables I want storage for. At the moment, this directive is more important for carpet than carpet X, but this is telling us I definitely allocate memory for that variable. Okay, that was another bunch of talking. Is there questions?
There are no questions in the chat or raised hands.
Look, it's only early in the morning for me, right? You guys,
yes,
you guys are supposed to be
some evening. Yeah, we
supposed to be
fully
awake.
awake. Yeah.
But seriously, I know that you must have some things about this you don't completely understand. But again, ponder on it, try and figure things out. Talk to us. Okay. Now, parameters. We have to decide what kind of parameters we want to use in our calculation. And in this case, this particular thorn example, we've got a number of them. So we've got a keyword parameter. Now, if you want to specify a keyword that says that the user is required to it can only have one of these, but you're going to give them a default. All the parameters always have defaults, so they don't none of them are obligatory, right? They all have defaults. In this case, I want to either do a standing wave or a Gaussian, and I picked standing wave. I can have as my default. I have an initial amplitude for my waves, which can be anything. So star colon star is going to say from anything to anything. And there's supposed to be a comment here, but in this case, the comment is just a blank string. And then my default is 1.0. And then for my kx, ky, kz, my defaults are 0.5. And these are just the wave numbers in the respective directions. And yes, question.
Steve, you have a question in chat.
I have a question in chat.
Yes, it says that where are the functions that are scheduled in the schedule file defined? Is this also done in the Torn?
Yes, I'm getting to that. So in a moment, after we create these CCL files, I'm going to show you how to create the corresponding source files. So just stay tuned. All right. So I can also specify an integer parameter like this. And then here's another boundary condition. This is another, so this is another keyword. This tells us what kind of boundary conditions you want. And there are various options there. Okay, so I'm going to create that. Any questions on param.ccl? Okay. Now for carpet X, you need a configuration that requires loop. That's pretty much what you're always going to want for that, and it's going to be just a bit of boilerplate. Now there is a possibility, like if you need to do something weird or special that you need access to, say, the MPI headers, you should require MPI in this section in order for that to work. All right, now the source code that goes with these things. So in this file, this file is going to be called init.ccx. So CCX for C++. And the function that I'm going to worry about here is this one. Okay, it's wave equation initial, and that is an extern C function with a void return type. It takes CCTK arguments, which is a macro. It's got declare CCTK arguments X, wave equation X initial. So it's got the name of the function is repeated at the end of this macro name because it's a per function macro. And then I'm going to have the parameter declaration. Now, if I scroll up to that schedule file, which is the question, you see wave equation initial. Now I'm writing the source code for that. Okay. All right. And so for these macros to work, I need to have these things included, right? And this is going to be, these other things are going to be needed for the looping and so on. And in this file, I'm going to have, most of this, credit to Eric Schnetter, by the way. I copied and pasted this and edited it down to simplify it a bit. but this is mostly his code. So this is our standing wave initial data problem, right? What we're going to do is we're going to take, we're just going to compute using cosine and sine and the wave numbers and pi and so forth to compute a value for u and rho. And these are all passed in as template parameters. And this is sort of the high-level mathematical code in comments here. And likewise, we have that for the Gaussian, right? And then in wave equation initial, what I have is loop int device. So this grid, as well as the u and v functions, are pre-declared for us. This is not pre-declared in CarpetX currently, but I think it needs to be. So the idea is vertex-centered grids are 0 and cell-centered are C, and that's 0 and 1. And because I've defined these two constants, right, I can say that I want to have a loop over the interior, that is excluding ghost and boundary zones. Device, I want it to run on the GPU if possible. And I want everything to be vertex-centered. Now, this loop int device is a function. The first argument that we're going to pass is the ghost zones, and that comes to us from grid. And then I'm going to have just some boilerplate here where I have where I'm defining a C++ lambda function. So equal means copy. One of the things that you can't do with a GPU is put an ampersand there for reference. You can't get references of things. You have to get copies. GPUs just don't allow you to work any other way. And then you have some other macros which are just a bit of boilerplate, which you can just always use. And this is going to call the standing wave function with various parameters, and it's going to update. Now, p.x, p.y, and p.z are going to be those are going to be the x, y, and z coordinates, and u and rho are the variables, and p.i is going to be what's used to index that variable. So instead of sort of indexing variables in the normal C way with square brackets, we're going to use operator parentheses and this p.i, which is the index in this point desk data structure that comes to us from loop. So it might look a little cryptic, but no more than any other C++ code. But this is the basic way that you write a loop to set up initial data. In other words, you call one of these looping functions, you specify the region, the centering, and then you provide a lambda function. And providing a lambda function like this tends to be what the GPU wants. So in this case, we can either use the standing wave or the Gaussian. In either case, we're just calling these functions we already looked at. All right, and I'm going to save that file. Are there any questions about this file? It's hard for me to really believe that there are no questions about all that.
It seems that everybody understands everything.
Everybody understands. You know what? I'm sure that isn't true.
Yeah.
But shyness is a problem we can't solve with the Einstein Toolkit software. But I think it's a good shyness is a good thing to lose.
Maybe I could ask a quick question.
That would be great.
It's about the grid.ngoszones line. Could you just maybe explain a little bit more why this line is included? So are you specifying that it's going to loop over the growth zones as well?
No, what I'm doing is I'm telling it the number of ghost zones. So I want to loop over the interior, and so that means it's going to exclude these many zones.
Okay. And so it's CarpetX is keeping track of the which cells are ghost zones and which cells are the interior. And by putting it in there, you're just telling it to not touch the ghost zones.
Right, or the boundary zones, as the case may be.
Oh, the boundary zones. Okay.
Yeah. Ghost and boundary zones are kind of similar things in that. So when we take so the way these codes work is they use finite differencing to compute derivatives, right? And finite differencing means you have a stencil that looks at cells on either side to compute the derivative. And by excluding the ghost zones, if we have a derivative, say, then we avoid the problem. We avoid the problem of indexing outside our array, right? We always keep a little buffer around us that's either a ghost zone or a boundary zone as a buffer, so that our stencils are always valid. All right, and this is determined at runtime, and then this will keep it all straight. Thank you for the question.
No worries. Maybe just one more then. If I wanted to loop over all the cells, including the ghost zones and the boundary zones,
You could loop all device instead of int device. So
okay.
int is interior, not integer.
Okay. Okay, thank you.
Thank you. All right, so this gets our initial data set up. Now we're going to evolve. And again, I'm going to define these two constants, and I'm going to do everything in terms of those. In this case, we had a parameter that is FD order, and that is our finite difference order. And this particular thing supported 2 or 4. And so in this case, I'm going to calculate either the second or the fourth order stencil. And this is just sort of done longhand explicitly. You know, if you've done second order finite differencing before, you might be able to recognize it in this code. Now, I told you before that when you just want to index something, you use p.i. Well, what if you want to do a stencil and you want to index a little away from the center? And in this case, what you do is you have this p.did. So p.i is actually a vector of 3 integers, right? And it's going to be, you know, 137, 54, whatever it is. It's the index into where you are in the grid. P.di0 is going to be 1 in the x direction. And P.di1 is going to be 1 in the y direction. And P.di2 is going to be 1 in the z direction. And so I can create a stencil where this is P.i minus 1 in the direction d, where d is 0 to 2. And this is plus 1 in 0 to 2. So what I'm doing a plus equal in this case, and I'm adding up the derivative in the x, y, and z directions. And then once I've accumulated that in DDU, I can assign it to the row RHS variable. And I assign it by using that same parentheses with an index that I've always used in here. Is that clear? Does somebody understand that? All right, there's somebody who understands that. I will, and of course, if I want to do a fourth order stencil, then I'm going to have a 2 times p.di because I'm going to go one further grid point away. All right. Yes, question.
So the p.x, for example, that's returning the x coordinate. That's the x. Okay. And I is the
Correct.
index.
Yes.
Okay.
And all right. So here is we're going to update our so here we're looking at boundary conditions, right? So there's a couple of different boundary conditions that were available to us. And I don't want to go too much into the details of boundary conditions, but this is the basic way that you do it. So you've got p.bi is kind of like p.di. It lets you know if you're in a boundary region. Now, there's some funny technical business going on here. Normally, the boundary region is the outer regions of the grid, and Amrex has its own ways of managing that, and it wants to do things specially there. And it doesn't give us as much freedom as we'd like. So if we want to use a standard boundary condition that Amrex supports, we can do that, and we don't have to worry about this nonsense. But if we want to write our own boundary condition, then we have to sort of make a second boundary layer inside the grid. And if you want to know if you're in that boundary layer, you can use this bi variable on point desk. And this D is the dimension. It's again going to go 0, 1, 2 for X, Y, and Z. And I can compute the value at this boundary zone. I can compute the value at this boundary zone using special logic if I want to, just by examining this. Again, I don't want to go too deeply into the weeds on this because when I run the example, I'm not going to use one of these boundary conditions. I'm going to use the standard one, but I just wanted you to see the .bi so you understood, at least at a high level, how that works. All right. And let's see. This is wave equation RHS. We have if boundary condition. Right. So yeah, we have a switch FD order to calculate the basic variables. And right. Okay. So are there any questions here? I'm sorry. Let me just clarify. So if I have the basic boundary condition carpet X, right, which is going to use the default Amrex stuff, then I'm just going to calculate the RHS as it is here. If I'm using one of the special boundary conditions, right, I'm going to either say here's the lower X, lower Y, lower Z, the upper X, upper Y, upper Z, and the interior, the normal interior. So I'm going to do sort of all three things at once in this view. And I'm going to do just the interior if I'm using the built-in boundary condition. Does that make sense?
So
Behan is nodding. Go ahead.
within the within the interior grid cell loop, it includes the boundaries as well.
Yes, through the conditional, right? Between I look for the lower boundaries, the upper boundaries, and everywhere else.
Okay. Okay. So it's like okay, so the loop itself, like so P dot I itself doesn't ever touch the boundaries. But if you use P dot BI, you get the
No, no,
interior
no, no, no. So what
boundary.
happens is P dot I goes into the boundaries, right? But the
Okay.
question is so every time this loop iterates, this point desk variable is set, right? And it's always got a valid PI. But the question that you have is, while I have a valid PI, am I in the boundary? And you can say, if this variable is less than 0, then I'm on the inner boundary. And if this variable is greater than 0, I'm on the outer boundary. But in all cases, I have a P dot I. Right? I'm just asking, this is just a where is my P dot I? And
Okay.
if I'm on the lower boundary, then I want to do this. And if where is my P dot I says I'm on the upper boundary, then I want to do this. And if my P dot I is not on any boundary, then I want to do this. Make sense?
Makes
Does it make
sense.
sense? Okay, good. Does it make sense to anybody besides Khalil? All right. There is another person for whom it makes sense. All right, so I'm going to
Yes.
write that file out. Yes, question.
No.
Okay.
There is no
All right.
question.
Okay. All right, so next what I'm going to do is I'm going to create my make.code.definition file. And this is kind of like a make file. And all I have to do to make this work is define this sources variable and set it equal to the names of my source files. In this case, init.cxx and evolve.cxx. And Cactus will do the rest. So let's do that. Now we've sort of created all the pieces of our thorn. So now what we need is a parameter file to make it run. And in almost every case, when you write parameter files, you're not going to write it from scratch. You're going to copy some other par file and edit it. So if it's a little intimidating to look at all the things in here, don't worry about it. As I say, you can copy parts of it. So, all right. These are the thorns we're using. We can add to this list at any time in here, but in this case, we've got them all at the front. So we're going to use carpet X, IOUtil, ODE solvers, and wave equation X. This is the thorn that we just wrote, this one at the bottom. And we're giving some parameters, some diagnostic information. Cactus has what is called presync mode. So presync is the system that keeps track of the consistency of the boundary/ghost zone regions of our simulation. And it has, there are two settings that work with carpet X, and there is there's presync only, and there's another one that has error in the name. You can always find out if you're interested in what the parameters are. You can always do source param.ccl, and that will show you the parameters of the flesh, the basic carpet infrastructure, right? And if I want to find presync in here, it's like this. So mixed error is the thing that we either need mixed error or presync only in carpet X. And mixed error is not going to try to do things automatically for you. It's just going to tell you if you screwed up. Whereas presync only will synchronize things automatically for you as you need it. And so that's the option. This latter option is what we're picking for this tutorial. And so we're having poison undefined values. This is just a debugging tool, which possibly costs you performance that you can strip off. And this is just giving you the number of cells that you're using. We're going to do a small simulation. This is our iteration count, and which tells us when Cactus will stop. You can do your termination in a number of ways in Cactus. So there's the final iteration number. You can use that. But you can say terminate. You can ask what condition to terminate under. By default, that's going to be your iteration, but you can also base it on, simulation time or some other thing.
Steve, you have 5 minutes left before the next tutorial.
Oh, geez. Okay. All right. All right. So we have this cool thing where we make our own thorn list. So you've seen how massive thorn lists can be. What we're going to do here is we're going to make a cut down thorn list that just has the bare minimum of thorns we need using this make thorn list script. We give it a master thorn list to work from. We give it our par file or par files that we want to run, and then we give it an output file name, and it will generate that thorn list for us, right? Once we have that thorn list, we can compile using just that set of thorns, and then we can run our simulation. So I will remove the wave equation thorn that we normally, or the wave equation in the simulation directory, so that I can run this thing. And then I'm going to submit with a create run like I did with Hello World. Peter's going to show you another way in just a few minutes. And then we have some visualization of the output, which is just going to be based on simple matplotlib plot.plot things. It's just going to show you a line plot of those things. So that's the super brief update of that. And you can see these cells are completing as I'm talking. So we created the thorn list. We built, we're building now, and then we're gonna run in just a minute. Questions?
If you have any question, you can unmute yourself. Sorry to interrupt.
Yeah. You could just don't be sorry. You can just unmute yourself and you can ask a question. And if you're running this and you come back with a question tomorrow, I'm probably only going to join in the afternoon on these things, but you can always ask us questions then. And there will be some of us around at all times probably. And all right, so here's my run, and this is this CarpetX startup, which got mangled a little bit by the output in the cell, and it finished. And look at that, there's my standing wave. graphed in just the detail that I asked it to run in. All right. Question. Any final questions? All right. We've got 2 minutes to transition to Peter.